All right, so hello everyone. Welcome back to the course. Can anybody hear me? Can everybody hear me? All right. So either there's nobody here or my microphone's not working. Yes. Okay. We got two people. All right. Great. Hopefully there's more people, and hopefully the rest of you can hear me too. So, all right. So last class, so on Monday, we looked at top-down parsing, and specifically, we went over LL1 parsing. Earlier I talked about the trade-offs and the differences between top-down parsing and bottom-up parsing, and one of the downsides of LL parsing was that many grammars cannot be parsed with an LL parser, and specifically grammars with left recursion. But anyway, we looked at LL parsing. We learned some concepts like first and follow sets that we are going to also use in the bottom-up parser. But today I'm going to start looking at LR parsing, which is more powerful in terms of the grammars that it can parse. Okay, and so I want to start off, with this example grammar that I have here. It's very similar to the one that we had on Monday, but slightly different. So I've already augmented it. So we have that initial start rule. S goes to E epsilon, right? So that not epsilon, dollar sign. So the dollar sign is the end of input symbol. And so, this grammar generates words like, well, A, or A plus A, or A plus A plus A, with the dollar sign at the end, right? So you can think of this as the beginnings of a grammar for arithmetic expressions. Okay, and so, maybe as an exercise, you could try and do the LL1 construction for this grammar. It will fail, but you will see how it fails. And it will fail because it has this E on the left of a rule. And so, if I had an expression like A plus A plus A, the shape of the tree that this grammar would give you for this expression looks like this, and it's left associative, right? So we do the plus on the left first before the plus on the right. And so that the E here on the left of the right-hand side of a rule enforces that. And the way that this would show up in the LL1 construction is that when you go to build your predict table, you would have an entry that would have two or more productions. In this case, two production rules. And specifically, when I see this first A in the input, and I'm trying to expand an expression into something that starts with A, the parser would, I guess the correct thing for the parser to do, if you think about the derivation of this string, the correct thing would be to apply this rule twice, followed by this rule, right? So this rule twice to get the two pluses into our string, and then this rule. But the parser has to make that decision because it's a top-down parser. So if I, put the start symbol at the top of the tree, because it's a top-down parser, it needs to decide how to go from that start symbol to the input that it has seen so far. So to this A, right at the beginning when it sees the A, it needs to build this whole section, and the number of branches in that section depends on the input that is going to come later. Okay, But in the predict table, if you are in the entry for E and for little a, both of these rules make sense because both of these rules have a in their first set, right? So E goes to A, well, that starts with A, but E goes to E plus A, well, E can go to something that starts with A as well. So both of these rules make sense, and the LL1 parser doesn't know which one to choose. And in this case, it's supposed to choose this one twice and this one once, but it can't know that without seeing the rest of the string. So what we're going to do differently today is we're going to do a bottom-up parser, and the bottom-up parser is going to be looking at the string and building the trees up above it, without having to reach that start symbol or the root of the tree until the very end. So it's going to be able to look at the whole string or more of the string before it has to decide how to build the tree. All right, so and I'm going to start with an LR0 parser, and then gradually we'll move to an LR1 parser, and we will see what that means as we go. But I'll tell you now that this grammar, it is an LR0 grammar. Okay, it's not an LL1 grammar, as we just discussed. So you can't parse it with a LL parser, but it is LR0. So when we do LR0, we're going to be able to deal with this grammar. Okay, and later on, I'll show you grammars that are not LR0 where we need something more powerful. Okay, so if I'm going to parse this bottom up, remember that building the parse tree is equivalent to finding a derivation. And when I talked about top down and bottom up, the sort of the two ways to find a derivation. One way was to start with the start symbol and take derivation steps and hopefully reach the input. That was top down. Now with bottom up, we're going to start with the input and we're going to build up the derivation sort of in reverse, going from the input. And then our hope is that eventually we're going to reach the start symbol of the grammar. Okay, so if I'm just going to write out the derivation that we want to build. So our derivation, we're going to start with the input string, and at each and we're also going to be looking at the input from left to right. So we're going to be changing things on the left side first, but we have this production rule. This production rule that says E goes to A. So we can apply that rule in reverse to change this A to an E. And then I'm going to write the derivation symbol backwards to say that E plus A $ derives or directly derives A plus A $, right? And so, we need an algorithm that does this, but this is the derivation that the algorithm is going to go through. Okay, and then, when we have this, well, again, we can look at the right-hand side of our production rules, and we see that there is one that says, E plus A. So we're allowed to apply that rule backwards and get just E, and the $ is still there. Okay, and then finally we have E $, and there's a rule, so we can get the start symbol S from that. Okay, so we're building a derivation, but we're building that derivation in reverse, starting from the input and the hope, right? And we have to keep hoping that we're going to reach the start symbol at eventually. And we're going to incorporate that into the algorithm, right? We're going to make the algorithm only take steps that sort of preserve that hope. With the LL parser, we were taking any steps that make any sense at all, that aren't completely stupid or completely hopeless. And so there's going to be a similar thing here. Okay, so we have to maintain this hope that we're eventually going to reach the start symbol. But I want to write down an invariant. So an invariant that we're going to maintain, and I'll write it here. So, and I'll say invariant 1 because we'll have a second invariant afterwards. So invariant 1 is that the input, let's see, I can write it like this, so that alpha derives the input. Okay, so because we're starting with the input and working backwards, the current step in our derivation always takes us to the input, and the thing that we're hoping for is that we're eventually going to get to the start symbol. So for the LL parser, for top-down, the invariant was that the start symbol derives alpha, that alpha is a sentential form. Okay, stop me if there's questions, or ask questions if there's questions. So now, in the LL parser, we worked through like a general algorithm, and then I said, well, our algorithm has alpha in it, and we want an efficient data structure to maintain alpha, and we transformed the algorithm by adding a stack to represent alpha. So we're also going to use a stack here, and in particular, we're going to each of these is one of the values of alpha, and if you kind of look at what's going on here, well, it's sort of on the left side of alpha where things are changing, where we're applying rules. And we always want to apply production rules on the left side. And then, the rest of it is the input that we haven't processed yet. Okay. And so the way that we're going to represent alpha is using a stack for the data here that can include non-terminal symbols in the grammar, like E. And then the rest of alpha is going to be just the rest of the input that we haven't seen yet. Okay, so I can rewrite this invariant to say that the stack plus the unseen input derives the whole input, so the unseen part of the input. And whenever you have a stack, I need to indicate the top and the bottom of the stack. And in this case, the top is going to be on the right side, because the top of the stack is where the changes are happening, right? So we're always representing alpha with some part of alpha is on the stack, and the rest is whatever part of the input we haven't seen yet. And now, there's going to be two basic kinds of operations that the algorithm is going to do. One of those operations is to take a part of the unseen input and move it to the stack, right? Push it onto the stack. And then that doesn't change alpha. It just takes something from here and moves it to here. And that's called a shift operation. So it's kind of obviously correct because it's not changing anything about alpha, but it's not very useful because it's not really doing anything. And then the other operation, which actually does change alpha, which takes a step in the derivation, is when we apply one of these production rules. And we're applying a production rule in reverse by finding the right-hand side of that production rule at the top of the stack and popping that off and pushing the left-hand side back onto the stack. Okay, and so that operation is called a reduction operation. And so now, we just need to put that together, and the algorithm is just going to be doing reductions and shifts at just the right time. And just to illustrate a bit more with this example, so I'm going to, draw a red line like this as the boundary between the stack and the unseen input. So, think of the red line as this plus here, the boundary between the stack and the unseen input. So at the very beginning, we start with our stack being empty, and the unseen input is the whole input, a plus a dollar sign. And then, we could look to see whether the top of the stack matches any of the right-hand sides of the rules, but the stack is empty, so it doesn't. So we can't do a reduction step, but we can do a shift step. And a shift step says, take a symbol from the input and push it onto the stack. So I'm going to move this red line over to say, well, now the stack is A, and the unseen input is only plus a dollar sign, right? It's not unseen anymore. We saw the A, and we pushed it onto the stack. All right, and then now we look at the top of the stack, and it is an A, and so we can apply this production rule and pop off the A and push on the E, and so then we will end up here, right? The stack will be we'll have just E on it, and then the input will have plus A. And so then you would do two shifts. So you would take two symbols, one after the other, read them off the unseen input, push them onto the stack until you're here. And now, the top of the stack matches the right-hand side of a production, so E plus A. So we can do another reduction and get to here. Okay, and at this point, you might notice that the top of the stack, it matches E plus A, but it also matches A, right? So, another possible reduction would be to change the A to an E, following the third rule in the grammar. And then our alpha would be E plus E dollar sign. So we would have E plus E on the stack. So far nothing prevents us from doing that, but that's sort of clearly the wrong thing to do, because then we won't be able to reach the start symbol anymore, right? So E plus E dollar sign is not a sentential form. There's no way to derive E plus E dollar sign from, or at least I hope there's no way. Yeah, no, there's no way. If we made that wrong turn, we won't be able to reach the start symbol. Okay, so we're going to need to make the algorithm smart enough to choose the right rule to reduce by, and to reduce at the right times. Okay, but if we choose the right one, we would pop E plus A off the stack, push E in its place. So now the stack is E, and then the rest of the input is dollar sign. And so, and if you wanted to take one more step, you could shift the dollar sign on and do one more reduction and get the start symbol. Okay, so now let's sort of write down the algorithm and look at how we're going to make the right choice of when to reduce and which rule to reduce by. So any questions at this point? Okay. All right, and I want to try to fit the algorithm down here. So, I mean, I'm going to just erase this last step just to have a bit more space for the algorithm. I mean, that last step is pretty trivial. Okay, so here's the LR parsing algorithm. So what we're going to do is we're going to look through the input from left to right. So from each A in X $. So once again, I'm assuming X is our input string. And then, right, so we're either going to push or we're either going to shift or we're going to reduce. And so I'm going to, first do a while loop that is going to do a bunch of reductions. And then once I'm done doing reductions, I can do a shift, and I'm going to shift this particular this A from the input onto the stack. All right. And for this while loop, I'm going to use a magic function called reduce, just like in the LL parser, I had this magic function predict that would tell me what to do, and we'll see what goes into the function in a little bit. But this function is going to take as input the current stack. Okay, so it's going to look at the stack, and it's going to use the stack to decide, should I reduce or not, and which production rule should I reduce by. Right. So, for example, if the stack is E plus A, it's going to say, well, reduce by this second rule. Okay, so this function is going to return, and again, it's going to be a set of production rules for which, it might be not a terrible idea to reduce by that production rule. But for an LR0 grammar, this set is always going to be a singleton set. So it's always going to have one rule to reduce by. And then, so if reduce says to reduce, we're going to reduce by that rule. And to reduce by that rule, the idea is to pop gamma off the stack and push A onto the stack. Right? So we want to pop the right-hand side of the rule off the stack, and we want to push the left-hand side non-terminal symbol. And I've got a question. Aha. Okay, good question. I'll do the question in like a minute. All right. So before I sort of look at the question, I guess lots of times people ask about this part, what does it mean to pop gamma off the stack? And what if the stack contains something other than gamma? Right? What if the stack has a bunch of weird symbols, and yet the reduce said reduce by this rule? And the answer there is, if reduce is correct, then it's only going to suggest this rule if the top of the stack actually matches gamma. Okay, so when I pop these symbols off the stack, I really just need to pop however many symbols there are in gamma. So in this case, I need to pop three symbols off the stack. So I'm going to say pop size of gamma times, but reduce won't tell me to use this rule unless the top of the stack actually is E plus A. Like, we're going to have to, when we go to implement reduce, we're going to have to make sure that the top of the stack actually is gamma in those cases. Okay, and now I've got a question from Neil, and so the question is: would the best strategy be a maximal reduce, like in Maximal Munch, so a greedy reduce, so where we do a reduction as soon as the stack matches the right-hand side of a rule, And I guess to decide between two production rules, we would take the longest rule. And okay, and so the answer is no. That's not always the right choice. And to expand on that further, notice that the input to reduce is the entire stack. Okay, so reduce actually gets quite a lot of information. It can use the entire stack to make a decision, and the right rule to apply depends on what is on the stack. And I can take us back to the example I had of a plus a plus a, right? And the idea there is, the number of times that we want a plus is 2 for this example. So we want to use this rule twice, but this rule once. But to know that we want to use this rule twice, we need to know that the input has 2 pluses. And so it's actually the part of the stack before the handle. Sorry, I should say that the right-hand side of a rule, when it appears on the stack, that's called a handle. I don't know where to write that, but okay. So this gamma here. Here we go. All right. The gamma is called a handle. So the idea is we want to make that decision not only depending on the handle, but depending on what comes on the stack before the handle. Okay, and so sort of the general thing is it for this grammar is we want to reduce an A only if there is no plus before it, and we want to reduce E plus A if there is a plus in there. I guess that is really, well, I don't know. I mean, here in this case, the handle would be A, and we're looking at what comes before the A on the stack. Okay, but that's a good question. So yes, thank you for that. All right. So if anyone has other questions, ask away. So a maximal strategy would also handle this. So for this grammar, yes. So for this grammar, if you can reduce by this, then I believe it is always the right choice for this particular grammar, but not in general. And the other thing, you might also have grammars where you have multiple production rules that both have E plus A as their right-hand sides, right? And then there would be no sort of maximal right-hand side because you'd have 2 production rules with the same right-hand side. Okay, so maximizing the length of gamma, you could have 2 rules with the same length of gamma. So for this grammar, it works, but not in general. Okay, so once we're done reducing, I'm going to push A onto the stack. All right, so I'm gonna, where's that red one? All right, so over here, this is my reduction step, and this is my shift step, right? I'll put it as a comment. So here, I'm taking this A from the rest of the input and pushing it onto the stack. And then I'm done. All right, so here it says, take that next symbol from the input, push it onto the stack. We'll go around the loop again, and we'll try to see, can we reduce now? And if we can, okay, we'll reduce. Otherwise, we'll do another shift of whatever the next symbol on the input is. Okay, and so, I mean, this is the algorithm that we'll follow. One thing that should make you suspicious, right? If you have any algorithm, it should have some output some way to succeed or fail. And uh-oh, sorry, my screen is locking. Okay. So so how can this ever fail, right? It's a loop, it runs and it completes, and it always succeeds, so that should make you suspicious. And what we're going to do is we're going to put a possible failure right here. And so let me just write the code, and I'm going to say if reject, and reject is going to take the stack. Well, it's going to take the new stack. So I'm going to say it's going to take a string or a sequence that has the stack plus a pushed onto it, and if reject is going to be another magic function, and if it says to reject, it's going to we're going to give an error here, right? And we're going to say, well, if you have an input that is the input you've seen so far, but also with a added to it, there's going to be no way to parse that. Okay, and so reject is going to determine that by looking at the stack. It's really running on the stack that we're about to get, right? What is the stack going to be after I push the A? If you get a stack where reject determines that there is now no hope, right? There's no way. We have this invariant, so we have alpha derives the input, but we get to a stage where the start symbol of the grammar no longer derives alpha, right? So if you get to an alpha where there's no way for the start symbol to derive it, then the algorithm is doomed. It's never going to reach the start symbol of the grammar. So that's how we decide to reject. And just like reduce, reject is going to be a magic function that we have to implement. Okay, and I've got a question. Where is it? One more reduction. Yes. Okay. So if you don't reject, then once you get to the end of this loop, the stack is always going to be stack is okay, and I want to say it. Okay, I want to say the stack is $, but in our example, it's $. So let me write it as $. So the point is, the stack is always going to be the original non-augmented symbol plus the end of input symbol. If I reach this point. And okay, why? Well, because the $, is a fresh symbol, so it can't show up anywhere other than the end of the input. So, and I just pushed A, and it was the last thing in the input. So that's why the stack has to end with $. And the only the only string for which reject will not reject, so for which we won't reject, that has that $, on the end is $. So in other words, we'll make reject reject every input that starts with a $, except if it has that start symbol on it. So once you get to the end of this loop, you could do an extra reduction, right? So do one more reduction by S goes to $. And most implementations don't even bother doing that, because sort of your original grammar would have been in terms of E as the start symbol, and this is just an extra rule that you've added to augment the grammar, right? So it just depends on whether you want a parse tree that's rooted at E, or a parse tree that's rooted at S with this extra augmenting rule as an extra node in the tree. Okay, but yes, to get all the way back to S, you need one more reduction at the end. Okay, so I've got the overall algorithm, and now the key is really just to implement reduce and reject, and then we'll be done, right? And so, but I mean that's where all the fun is, or all the interesting stuff is. Okay, so I'm going to look at that, but any more questions before we go there? Okay. All right. Let me make some space here. All right. So I mean, I talked about hope, and the thing that we're hoping for is, and I can do dashed lines, right? So the thing that we're hoping for is that the start symbol of the grammar derives alpha, right? That's the hope. And so we're going to base our invariant 2 on that hope, right? So and so sort of one thing we could try to do is say, well, why don't we just make invariant 2 say, well, S derives alpha, right? Let's make that our invariant 2. But that doesn't work because, if I had invariant 1 and invariant 2, for invariant 2, if I said S derives alpha, then we would know that S derives alpha and alpha derives the input. And so that would mean that the input has to be a valid input, right? It has to be in the language defined by the grammar. But, what if it isn't? Like, we don't control the input. Okay. And what's more, our alpha, we're representing alpha as the stack plus an unseen input. And sort of by definition, the unseen input, we haven't seen it yet. So we don't even know what that input is. So we can't know that, S derives, say, the stack plus the unseen input when we don't even know what the unseen input is. Okay, but what we're going to do is something related. So I'm going to forget about the unseen input, and I'm going to make an optimistic assumption about the unseen input. Right? I'm going to assume that the rest of the input is correct in the sense that it's exactly the input I want, or it's the most optimistic input that is going to make the parse succeed. Okay, and so for invariant 2, I'm going to need to make a definition, but invariant 2, I'm going to say is going to be that alpha is something called a viable prefix. All right, and so what's a viable prefix? So, and I'm going to be writing this a lot, so I'm just going to write it as VP. So a viable prefix is a prefix of some sentential form. Okay, so so when I say that my invariant is that alpha is a viable, okay, I messed this up. Okay, it's not alpha. I don't want to say that alpha is a viable prefix. I want to say that the stack is a viable prefix. Okay, and a viable prefix is a prefix of some sentential form. So I guess I could have said my invariant as the stack is a prefix of some sentential form. And remember back to, I guess it was last week, so what's a sentential form? A sentential form is something that is derived from the start symbol. Okay, so the invariant is that the stack is a prefix of something that is derived from the start symbol. And I can restate the invariant formally, so I can say there exists a beta such that the stack such that S derives the stack plus beta. Okay, and so here's where the optimism about the unseen input comes in, right? So if there is some possible, happy input that we could have in the unseen input, such that S derives the stack plus that input, then we have a hope that the real input really is that one, and S derives the stack plus that input. So we still have a hope of reaching S. On the flip side, if the stack is not a viable prefix, then there is no hope. No matter how good the rest of the input is, we're never going to reach S, and that's where we're going to give up. Okay, so this idea of a viable prefix is sort of a really key concept in defining reduce and reject. So once again, the stack has to always be a prefix of something that you can derive from the start symbol. Okay, so questions there. Okay, so now that we have this viable prefix idea or this invariant, I can define reject at least. Reject is going to be easier. How am I going to define reject? I'm going to have a green marker here, right? So reject, and I'm going to say reject of alpha is I'm going to whoops, it's not a set, it's a Boolean, and I want to reject alpha if it's not a viable prefix. So alpha is not a viable prefix, right? So basically reject is going to reject the new stack if it's not a viable prefix, because if we didn't reject, we would violate this invariant. Okay, so hopefully reject is sort of easy. If we would ever get into a state where we violate invariant 2, where the new stack is not a viable prefix, we're giving up and we're giving an error. Okay, what about reduce? And I'm going to try to get myself some more room here for reduce. All right. So reduce of some stack alpha. Now, reduce is supposed to be a set of production rules. So I'm going to make it a set. A goes to gamma such that, such that what? And, I already talked about how the top of the stack has to match the right-hand side of the rule, right? The handle. So I'm going to say there exists a beta such that beta gamma is alpha. So the stack is, some beta plus gamma. So the stack has gamma at the top of the stack, right? You only want to reduce if gamma is at the top of the stack. So, okay, so this part was kind of easy. Now the hard part, right? So I want to reduce only if I can maintain invariant 2, the invariant about the viable prefix. So I want to make sure that after I reduce, that whatever is on my stack is still a viable prefix. So I need to ask myself, what will be on the stack after I reduce? Well, I'm going to pop gamma and push A. So if my stack was beta gamma and I pop gamma and I push A, then I'm going to say that beta A is a viable prefix. Okay. Right. So any questions on that, right? So once again, I'm checking to make sure that the stack ends with gamma. And if it ends with gamma, I want to say, well, if I was to pop off gamma and push A, which is what I would be doing here with the reduction, then I want to make sure that I'm still obeying invariant 2. So I want to make sure that beta A is a viable prefix. Okay, so hopefully that definition for reduce makes sense. So now, what's left? Sort of what's the problem? Well, for both reduce and reject, I have to make this check, make this decision of, is this stack a viable prefix or not? Right? This stack or this new stack, is that a viable prefix? All right. So all I have to do is decide whether something is a viable prefix. So I'll write this. This is important. So need to decide whether, and I'll say whether alpha, but it's for any alpha, is a viable prefix, right? This is sort of our key question. If I look at a stack, I want to know, is it a viable prefix or not? Okay, well, how do I decide? Well, it's viable prefixes are things that are prefixes of sentential forms. So what are all the sentential forms? Well, I mean, there's infinitely many sentential forms in general, even for a tiny grammar like this. There's infinitely many viable prefixes of sentential forms, even for this very simple grammar. It's even actually the case that the viable prefixes of a grammar are themselves a context-free language. And I usually give this as an exercise. So given a context-free grammar, find a method, an algorithm to transform it into a grammar for the viable prefixes of that grammar. Okay, and generally it means taking the non-terminals and making them be extra terminals. So you're adding more terminals and then looking at making the grammar generate prefixes of the language that the original grammar did. So there's this transformation that you can do to take any context-free grammar and turn it into a context-free grammar for the viable prefixes of the original grammar. So the point is, the set of viable prefixes is a context-free language. So you could write a context-free parser for that set. And remember, what a parser does is it answers the question, given alpha or given some string, is that a string in the language of the grammar? So if only I had a parser, I could use that parser to decide this question, and then I could implement my parser. Okay, so do you see the chicken and egg kind of problem? That in order to implement a parser, I need a parser for viable prefixes. Okay, So, you know, I mean, this is bad, right? So to implement a parser, I need a parser to decide whether alpha is a viable prefix. And yeah, okay, so in general, this is bad. But, you know, oftentimes in computer science, there's things that seem impossible, but then you get some sort of solution or heuristic if you just try it anyway. So, you know, some problem is NP hard, but you try to code it up and it just runs anyway, right? Like if you've ever looked at SAT solvers, right? That's supposed to be NP hard, but they work really well in practice. Or some problem is undecidable, but you try to decide it anyway, and yeah, often it works. So not always, obviously, if it's impossible, sometimes it's going to be impossible. But in this case, we're going to try and decide this anyway. And what I'm going to do or hope for, you know, let's hope that the set of viable prefixes was a regular language and that we could build, well, in this case, we're going to build an NFA for that language. Okay, and we're going to fail because it's not actually a regular language, but we're going to try anyway, and you know, getting half of the way there is going to be enough to make our parser work. Okay, so here's my goal. So I want to make an NFA for the viable prefixes of this grammar. And let me just see what I can erase and what I can't erase. All right. Okay, so I want to erase all this stuff. So any questions before I go erase a lot of stuff? All right. All right. So, okay, so I'm trying to build an NFA for the viable prefixes of, and I'm going to do this little grammar here, this little example grammar. Okay, so what are the, well, okay, so what are some viable prefixes first? I know, you know, let's do that over here. So S is a sentential form. So any prefix of S is a viable prefix. So the empty string is a viable prefix. S is a viable prefix. And then we know that S derives E $. And so any prefix of that is also a viable prefix. So, you know, empty string, E, and E $, those three are viable prefixes. And I'll do like a little bit more here. So E can expand to E plus A, oops, E plus a $, that's a sentential form, but also to a $, that's a sentential form. So any prefix of any of these strings is a viable prefix. And, you know, I could go on, right? I could expand this further into more sentential forms that have more viable prefixes. Okay, and so I want to do an NFA for these. And all right, so let's let's do an NFA. And so I'm going to have a start state for my NFA, and I'm gonna skip the S part. I'm going to focus on E $. So I want every prefix of E $, to be accepted by this NFA. So I'm going to have an accepting state as the start state for the empty string, and then I want to accept E. Okay, I'm drawing the states in a rectangular way, just because I'm going to be writing things in them, but you could write them as circles if you wanted to. Okay, so E I want to accept, and E $, I want to accept. All right. Okay, so, you know, so far I can accept, you know, empty string E and E $, the viable prefixes of this particular sentential form. And, you know, as I'm drawing this, I'm going to label the states. And sort of a way to label them that will become convenient is to use the production rules with a dot on their right-hand side. So I'm going to say, the way that this $E$ came about is from the start symbol, I applied this production rule, and now I'm at the very beginning of applying this production, or at the very beginning of the right-hand side of this production rule. So here I have skipped over the E, so I'll put a dot there, and then here I've got $E$. Okay, but I mean, again, it's the structure of the NFA that matters, not really the labels. It's just that this is a standard way of giving names to these states. Okay, great. So I've got the prefixes of one sentential form. But now, I've got two ways that this sentential form can derive other sentential forms, right? E plus $A$ or $A$. And these two ways stem from the fact that I have this this edge here, this transition in my NFA that has a non-terminal symbol on it, this non-terminal symbol E. And really, every time in the grammar that I see an E show up, I'm always allowed to apply these two production rules to that E. Okay? So in other words, in my set of viable prefixes, if there's ever a viable prefix with an E in it, then replacing that E with E plus A, or replacing that E with plus A, should also give me a viable prefix. Okay, so the way I'm going to encode that is I'm going to take this edge, this transition E, and instead of going through an E, you can go through A, right? So following the last production rule in my grammar. And so I'm going to write this as E goes to dot A, and I'm going to, well, again, maybe the labels on the states are distracting at this point, so maybe ignore the labels for a second. But I'm going to make these edges here, and then I'm going to put epsilon transitions to here. Okay, so every time I have a transition with a non-terminal symbol on it, like here, like E, I'm going to, add some states for the right-hand side of that production rule, and then I'm going to use epsilon transitions to say, well, you can either take the E, or instead of the E, you can go down here, take the A, and then come back. Okay, and I'm going to do that for the other production rule as well. So I'm going to have E goes to dot E plus A. And on an E, this is going to go to E, goes to E dot plus A. And then on a plus, it goes to E plus dot A. And okay, and then finally on an A, it goes to E plus A dot. Okay, and I need to connect these with epsilon transitions. So epsilon. So instead of following this E, you can go here, do the E plus A, and then come back. So epsilon transition like this. Okay, so this is the way I'm going to build my NFA. And once I've added these states, I can now handle prefixes of these other two sentential forms. Okay, and for completeness, I should probably add some more states for the S at the beginning. Usually we don't even bother including that in the NFA just because the S is the special case, like it's only at the very beginning of the derivation. But if it makes you feel better, feel free to, add one more. Where are we here? How would I do that? From the start state, well, anyway, from the start state, I could go to an accepting state on the S. But usually we don't bother putting that in. Okay, so I can now, my NFA now can handle all prefixes of all of these sentential forms, but here I can take this E and expand it further, right? So, and the where that shows up in my NFA is that I have this edge here, which has an E on it. And remember the rule I told you was, well, whenever I had an edge with a non-terminal on it, I would look in the grammar and add these states to expand the right-hand sides of that non-terminal and epsilon transitions to kind of take me back and forth. So I should do the same thing for this edge E here, which means I would have to go and add another pair of states here, right, for this rule, and another sort of copy of these states, and I would add epsilon transitions to go to them and back from them to sort of model this E edge. Okay. Do I have a bug here? Yes. Thank you for the typo. This should be E goes to A dot. Yes. Okay. So the dot jumps over the A when you transition on an A. Okay. So to expand this E edge, I would have to, make another copy of this down here. And then that copy of these extra states would itself have another E edge like this, right? And so, if I repeat that forever, then my NFA becomes infinitely large. And of course, the F in NFA stands for finite. And so it's not supposed to be infinitely large. Okay, so, but if I wanted an NFA for all the viable prefixes of this grammar, it would have to be this infinitely large NFA. And so that's a very, a very hand-wavy proof that the viable prefixes of this grammar are not a regular language. Okay, so this is where we failed, right? We can't build an NFA for the viable prefixes. But, right, but what? So, okay, and I didn't erase this part. I erased the other green part of what reduce was going to be. But the point is, we're asking, is alpha a viable prefix? And alpha is the new stack. Okay, here, we're also, we were asking whether beta A is a viable prefix, and beta A is the new stack, once you reach here. So we're only asking this viable prefix question about strings that ever show up as stacks in the algorithm. Okay, and the set of all viable prefixes is not a regular language, so we can't use an NFA for it, or it would have to be an infinite NFA. But if we limit ourselves to only those viable prefixes that ever come up as a question in this algorithm, this NFA is actually enough. Okay, and let's see why that is. Right, so I'm gonna sort of hypothetically, right? Let's say I was to add this epsilon transition, and then I had this extra thing with the A. and then I had an epsilon transition back. So, let's look at this pair of states and this pair of states. So their structure is almost identical, right? They're both, well, there's two states, they're connected by an A transition. And really the only difference between this pair of states and this pair of states is this epsilon transition, right? Here, the epsilon transition from the second state goes to this state. Here, the epsilon transition from the second state goes to this state. So the only difference is that epsilon transition. And that epsilon transition is why I need to make a new copy of these states to account for this E edge, rather than just reusing this copy. All right. So if that epsilon transition wasn't there, so let me cross it out. So if those epsilon transitions were not there, then what could I do? Well, instead of creating two new states here, I could instead just reuse the states I already have. So I can make an epsilon that goes to this state that's going to, see the A. And then, the only difference between this state and this state is the epsilon that would take me here versus here. But if the epsilon was gone, then this state and this state are completely identical, and I don't have to introduce a new copy of them. I can just reuse the old copy. Okay, so if that epsilon transition, doesn't need to be there, then I win, right? Then I can have a regular language, and I can use an NFA. Okay, and specifically, the NFA that I would have is, so instead of this epsilon transition, I have this epsilon transition that goes here. And then similarly, normally I would have another epsilon transition to a copy of these four states. And, instead I can make that epsilon transition go to the original, those original four states, as long as this epsilon transition is not needed. Okay, so now my diagram is getting messy. So I'm going to erase the, erase the crossed out stuff. So I'm going to erase this part, and erase this part, and erase this part. Okay, and so now I claim that this is an NFA for the viable prefixes of that grammar that ever show up as stacks as my algorithm is running, or that the algorithm ever asks about. Okay, and the key is that for the stacks that the algorithm ever asks about, it has to be the case that they don't use that epsilon transition that I removed. Okay, and so, let's see why they would not use that epsilon transition that I removed. So the epsilon transition, it went from this state, and this is a state that says that the stack, well, like to get to this state, I start from the start state, and the stack has to be A. Okay, but the reason that I added this whole sequence of states here was that I had this E edge or this E transition in my NFA, and I had a production rule that said, E goes to A, right? Or I added these four states because I had an E transition and a production rule that said E goes to E plus A. And so if my stack is ever going to be such that I reach one of these states, so this state that had the epsilon transition back, or this state that had the epsilon transition back, when would I ever need that epsilon transition? Well, I would need it if I wanted to, go here, take the epsilon transition back, and have more symbols on the stack on top of the A, right? So if if my algorithm runs and it pushes an A on the stack, and then it pushes a $sign on the stack, that would be bad, because to be able to tell that the stack is a viable prefix, it would have to go here, see the A, take the epsilon back, and follow the $sign. So the point is, the algorithm is never going to push that $sign on top of the A. And why not? Well, because first, it always asks itself, can I reduce what's on the stack? All right. And remember, reduce is to say, well, if gamma was popped off the stack and A was pushed in its place, would that still be a viable prefix? But the reason that I have these this sequence of states that recognize gamma, so like this sequence of states or this sequence of states, was that I had a transition with A on it. Okay, so if the stack is ever such that I would reach one of these states with a dot in it, or these states that would have had the epsilon, reduce is always going to pick at least one production rule to reduce by, because if instead of that gamma, I popped that off and pushed on that non-terminal that led to the epsilon that started this whole sequence of states, then just following that original transition would take me to this accepting state. And so that would be a viable prefix as well. Okay, so if I ever have a stack that reaches one of these states, then reducing it would also give me a stack that reaches an accepting state. And so I will always reduce the stack, before I would ever be able to push anything more on it. And the only time I need that epsilon transition is if I were to push more on it. But I won't push more, because I'll reduce first. Okay, so it's kind of a complicated argument, but the argument is I will never reach a state that would require me to take one of those epsilon transitions, because I will reduce first, and therefore I don't need the epsilon transitions in the NFA, and that in turn enables the NFA to be finite instead of infinite. Okay, so these are all very subtle points. I think I've explained them as well as I can, but if there's questions, this is probably a good time to ask about this point. So think about questions and ask them if you have them. If there aren't any questions, I'm going to summarize the general construction of this NFA. So any questions? While I find my marker. Where did I put my marker? Okay, I got another one. Oh, there it is. Okay. Okay. So in general, okay, no questions? All right, well, no questions then. So in general, how do I build this NFA? Well, if you remember back about 3 lectures, how do I specify an NFA? Well, it's this 5-tuple, and I need to specify, each part of the 5 tuples. Let me kind of make some space here. Okay, so what's the alphabet of the NFA? Well, what are the symbols that I see on the transitions? Well, they're the terminal symbols and the non-terminal symbols of my grammar, right? So here's a terminal plus, here's another terminal A, here's a non-terminal E. So the alphabet of my NFA are the terminal and the non-terminal symbols. All right, what are the states of my NFA? Well, the states are going to be these, I have these labels for these states, and they're going to be of the form A goes to beta, alpha dot beta, such that A goes to alpha beta is a rule in my grammar. Okay, so whenever, for every rule in my grammar, I can split the right-hand side up into two halves, alpha and beta, and I put a dot in between the two halves, and these are the states of my NFA. These are also called the LR0 items. So you'll see them called items, the LR0 items of a grammar. Okay, but they're the states of my NFA. All right, what do I need? I need a start state. So start state Q0 is, and so I'm going to write this as, so I really want the augmenting rule of my grammar. So I'm going to write it as S prime goes to S dollar sign. The confusing thing is that for this example, S prime is S and S is E, but it's the augmenting rule of my grammar with the dot at the end, at the beginning. Okay, that's where my NFA starts. Accepting states. So all the states are accepting states. So A equals Q. So the accepting states of this NFA, you see double borders everywhere. This is the last time that I'm going to draw them as double borders because it's just annoying to draw them as double. But for all of these NFAs and DFAs that we're going to see, all the states are going to be accepting states. Oh, and I've got a question. What does the epsilon transition to the same state do? This one. Yes. Okay. All right. Yes. Good question. Thank you. So, okay. If I go back, well, I guess I'm going to write the general rule just now. But so this is like perfect timing for that question as well. So the general rule is whenever I see a transition with a non-terminal symbol on it, I go to my grammar, look at all the production rules that expand that non-terminal, and I create or I find the sequences of states for the right-hand sides of those production rules. So, in this case, this one and this sequence of rules. And I put an epsilon to the beginning of each of those. So here, because I see an E, I need an epsilon to here, and I need an epsilon to here for the two production rules. Here, I also see an E on a transition, and so I need an epsilon to here and an epsilon to here, because this is a rule that expands E. Okay, so that's why it's a loop. I mean, functionally, in terms of the NFA functionality, you don't. It's useless, right? You don't need an epsilon transition that takes you back to the same state. You can just stay in that same state. But for the general construction, you would have, because there's this edge on an E, you would have an epsilon transitions to the beginning of any sequence of states that's expanding E. Okay, and let me sort of write that down in general. Okay. So if I have a transition from A goes, so alpha dot B and a beta on an epsilon. Okay, so if I'm ever at a place where the dot is before a B, and a B is a non-terminal, so then I know that from here I'm going to have an edge out on that B non-terminal. And so I want an epsilon transition to every production rule that expands B. So I want to go to B goes to dot gamma such that B goes to gamma is in the production rules of my grammar. Okay, so that's the general thing of sorry, this is getting messy, I know. All right. Okay, and I've got one more row to put. So, and maybe I should have done that one first. But if I have alpha dot x, and this is a capital X, so I'll make it a bit bigger. So alpha dot x beta, and on an x, you want to go to sorry. Okay, it's A goes to alpha. Okay, so if you're in a state that's labeled with A goes to alpha and the dot is before an X, remember an X could be a terminal symbol or a non-terminal symbol. So basically the dot is in front of anything, then on that anything, you want an edge to a state where the dot jumps over the X, right? So from dot A, on an A, you go to A dot, or dot plus, on a plus, you go to plus dot. So that's just going to be A goes to alpha X dot beta, and that's going to be your state. Okay, so I guess this second transition is the sort of the obvious, the black transitions. The when the dot is before a symbol, you have an edge that causes the dot to jump over that symbol, reading that same symbol from the input. So that's this transition. And then this transition is the epsilon transitions. So anytime the dot is before a non-terminal, then you add an epsilon transition to every production rule that expands that non-terminal, and you want to go to the beginning of that production rule. So the dot is at the beginning before the gamma. Okay, so I guess this part got kind of messy, but sorry about that. Here's the general definition of how we create the LR0 NFA in general. Okay, so for any grammar, you can let's see. So for any grammar, you can go and build this NFA. The thing about it being LR0, you need to make sure that reduce here is going to give you at most one rule. So there's that catch there. Not all, for any grammar you can build this NFA, but not all grammars are going to be LR0, are going to be parsable this way. So to be able to tell whether a grammar is going to be L0, we're going to have to take this NFA and turn it into a DFA, see what all the sets that could come up are, and see if we're going to be able to parse that. So I need to leave until Monday's class. So on Monday, we're going to take this example, we're going to take this NFA, we're going to convert it to a DFA, run the example, try to make sure we understand how the algorithm works, and then look at what could go wrong in terms of the grammar not being LR0. Okay, so I'm out of time. If there's any more questions, I should answer questions now. But if there's no questions, I'm going to stop here. So anyone, questions? Last call? Okay, so have a good rest of the week and a good weekend. And we'll pick this up on Monday. We'll do the DFA, and we'll actually parse with this thing. Okay, all right, bye.